All of you are requested to switch off your microphone and activate our speaker and delegates present. Only our invited speaker can present their screen, except the invited speaker don't present your screen. Otherwise, it will be very trouble to switch the our speaker and other. So, our participants are requested to mute your microphone, camera also, because it is the camera, then the broadband, then the mic. And except our speaker, all don't present your screen. One is another request for participants. If any time you have reached the meeting or you have any problem to joining this meeting, then you can follow our direct YouTube link also. YouTube streaming also is started at 10:30. Gopinath Babu, please switch off your present screen. All the participants are requested to please don't present your screen. If you have present your screen in our interaction session and in our present session, then we have to do from our meeting also.
নাইটি পরে বসবি নাকি? হ্যাঁ, কলেজের নাই?
Please, Gopinath Babu, don't present your screen. You can follow our. welcome to all of our welcome to our one-day international level seminar in the research recent research trend in nanomaterials and device. So first of all is I have requested to our speaker and our principal sir to can you get my voice, uh, Dr. Montana Das and Dr. Kartik Ghosh and Samaris Das.
Yes,
Can you
yes,
get my voice?
yes, yes.
Okay, I have getting your voice, Dr. Sir. So now we are starting our seminar. So first of all, things I have welcome to all of our dear participant and the lecturers and the speaker and delegates and every people to join this platform and join our e-seminar. And we will be thanks to all of these people to come here and we have requested to cooperate with us for the successful running this conference. So just I have talked to more things. So please, audience are requested to their microphones and if it is possible that video camera also because if you use this microphone, it will be the audio reflection at itself. And if you use the video camera, then the bandwidth slow. So you are requested to completely switch both these microphones and the um, camera also. And being the presentation session, so only the speaker will be present the screen and other don't any people present their screen. So it will be very hazardous to compile both this screen. So except our speaker are requested to put up your microphone and video camera and don't present your screen also. So now I am requested to our principal sir, Dr. Monty Kumar Das, to inaugurate our seminar and and some welcome speech to our this seminar also. So someone is present their
Good morning,
screen. So Devasis Noskar, please
good morning
go
to
and present
everybody,
your screen.
respected participants and resource persons. It is indeed a unique, memorable moment for me today, the 11th August 2020. As at this moment, I am going to deliver my welcome speech as principal of Santal Vidrah Sardha Shatavarshiki Mahavidyalaya in the international webinars entitled Recent Research Trends in Materials and Devices. It is my great privilege to welcome Professor Kartik Ghosh, Department of Physics and Material Science, Missouri State University, USA. He will talk on nanostructures, materials for energy technology applications, and he has done his PhD from Tata Institute of Fundamental Research, India, and postdoctoral studies from University of Maryland, and he has published more than 170 papers in peer-reviewed journals, and he has been serving as reviewer in many reputed journals in abroad. And I want to mention that Dr. Bose is my classmate at BSc at Midnapur College, West Bengal, and MSc at Rajavaja Science College in the same year. So it is a great privilege to me that he joined as a speaker here and he will enlighten us with his valuable speech. I also welcome from the core of my heart Dr. Samaris Das, Associate Professor at the Center of Applied Research in Electronics, IIT Delhi. And he has published more than 62 papers in peer-reviewed journals and 2 patents. And he is the recipient of Young Engineer Award 2017 and Young Scientist Award in the year 2019. And he will talk on semiconductor nanostructure for electronic and optoelectronic devices applications. And he will mainly address our college teachers in the remote regions how to do experimental research at the remote places with minimum infrastructure. And I also welcome all my participants from different institutions, my beloved colleagues, and I am very much excited that many of my previous students have participated in this e-seminar and they are working in different fields as teacher, assistant professor, associate professors. And at the outset, I also want to mention that Dr. Somodesh is also associated with me for a long time. And I am fully confident that the valuable to be delivered by the eminent scientists will certainly benefit the students, research scholars, young teachers, and motivate to join hands with the scientists in future to develop a modern India with a advanced technology which will not be harmful to all. Finally, I must congratulate Dr. Kaushik De, head of the Department of Physics of my college, and Professor Arup Ratan Chakraborty, head of the Department of English and Secretary Teachers Council for arrangement e-seminars. They are working hard for holding this e-seminar. I must congratulate them. And with these few words, I again welcome all the resource persons and the party students, research scholars, and teachers from different institutions for in this e-seminar. Thank you very much. Have a nice day. And I declare the e-seminar is open. Thank you very much. Have a nice day.
So, thank you, our principal sir, to deliver his innovation and the welcome speech. Now, I am requested to Dr. Karthik Ghosh from USA. Is another great scientist in the nanomaterials and the nano device. So, I am requested to Dr. Ghosh to start your presentation and start your valuable lectures. So, all of you, other than Dr. Ghosh, you are requested to switch off your microphones and if it is possible, the camera also. So now the Dr. Ghosh.
So, can I share the screen? Let me see how to
Yes,
do that.
the
Okay,
lower
now,
panel, there will be the option for present the screen.
okay, let us see. You've given me access, right? I hope. Okay, let me see. Yeah, so just a minute. Yeah, I'm trying to see. Okay, present now. Maybe I got it. Present. Okay.
So Dr. Ghosh, you want to present the video camera. Please switch off your video camera.
Can you see my screen?
Yes, I have seen your face, so I have not seen your screen.
Screen? No. Okay, let me check again. Yeah. Okay. I thought I did. Okay. How about now?
Yes, I have getting your screen.
I'm getting my screen right. Okay, let me see that. Okay, so hmm, so what do you see now?
I have seen some buildings and some
Oh, okay.
button
So that means you are there.
include.
Okay. Okay. So you're there. Okay. So let me do. Okay. Okay. So I think you can see my slide, right? I believe you can see, right?
Yes, yes, I've seen it. Yes,
Okay. Is it clear, right?
yes, it is clear. If it is possible, then you can use the full screen also or some
Yeah.
bigger.
Yeah. I'm doing this full screen. It looks like okay. Okay. Let me show. Okay. So go through that. Right. Couple of slides. Okay. So you're seeing, right?
Yes, yes, I've seen.
Okay, so let us start again. Thanks to Dr. Das, particularly again Muntu. He's my friend, classmate, and we are again, from the same college. Uh, so we did our BSc, MSc, and sociology. Whenever I come in Minapur, I try my best to meet with different colleges and sociology. It's my pleasure to give some presentations, and particularly for students and young teachers. Hope it will help, and I'll try my best to go to low level as low as possible so that you can get it. And always feel free to ask questions. Okay, so now here, so I think let me start from where I am. So surely, I think most of you know that I think told me that I can talk in Bengali too. Okay, hopefully, if that helps, right, with the mixing Bengali and English. Okay, so I think all of you know about well-known place, the Chicago. I think I am actually 500 miles southwest of Chicago, and so this is actually our university campus, and this is my lab. Although you'll feel good that this lab, whatever you see that lab, actually I just got this specific instrument for my research imported from India. Okay, so that means the idea here, India can make many things. It is not like just USA থেকে ইন্ডিয়াতেই এক্সপোর্ট হয়, কিন্তু ইন্ডিয়াতেও অনেক ভালো ইনস্ট্রুমেন্ট পাওয়া যায় এবং অনেক কিছু করা যায় আর কি। হ্যাঁ, specifically this instrument I got it from my friend. Okay, so friend means he was my colleague at TIFR, but later on he moved to the company. He has about 100 employees, and so he right now I think he distribute most of his instrument all over India, and socially he export also in other countries. So I may be the first or second person imported actually from India. And still, a good thing is that these two instruments, I got it in 2004. Right now to 2020, but still it works really great ways. Okay, so again, I'm talking more materials aspect. Anything on future depends on how good materials you make. Major, applications related with good physical properties, and that physical properties is dictated by good materials. Every day, actually, people are working on to find new materials. So surely one of the aspect is you can find the new materials, or the other aspect is that you have the same you have the existing materials, but you can change the size. Okay, so that's why the basically called nano. You go from micro to nano, or maybe sub nanometer level. Okay, so in that case, actually, again, the idea is to change the properties. মানে কিভাবে প্রপার্টিসটা চেঞ্জ করা যায়, প্রপার্টিসটা হচ্ছে মেইন, প্রপার্টিসটা যদি আমরা ম্যানিপুলেট করতে পারি, দেন উই ক্যান হ্যাভ গুড ডিভাইস। ইউ হ্যাভ টু কিপ ইট ইন ইউর মাইন্ড যে আমরা কিসের অ্যাপ্লিকেশন চাই। ডিপেন্ডিং অন দ্য অ্যাপ্লিকেশনস উই নিড টু নো অ্যাবাউট দ্য প্রপার্টিস, অ্যান্ড ডিপেন্ডিং অন দ্য প্রপার্টিস আমরা we need to have materials. So that's why actually the nanomaterials has last decades. Is trying to all over the world actually focusing on nanomaterials because it actually, you can manipulate the material. So anyway, we'll talk about that. And that aspect, again, you can start with the simple gold materials or any materials available. You can find out, you can actually manipulate a lot of stuffs, and it's possible to do that. Okay, but here I get focus, which is just we'll talk about nanostructured materials for surely, again, as I said, always you have to keep it in your mind that what could be the possible applications. And so surely you'll be doing the science behind it, okay? So that means I'll talk, one thing is the nanostructured materials for application to clean energy, okay? Because I think all over the world, people are looking for sustainable and clean energy. So that means how nanostructuring can help to improve the energy technology. That basically I'll talk about it. So surely one of the things is that, again, whether you have a physics or chemistry or biological background, everywhere actually nano is, if you want to do nano, physicists, chemists, biologists, engineers, everybody can do that. So then the question is why nano? One of the things is that I think all of you know about atom, and I think whatever you see day-to-day life, bulk materials, it's called bulk materials. And then when it surely atom, you don't see it by your eyes or anything, but it's just visualize, you know that materials is made of atom. But then if you have few atoms, right, or a couple of thousand atoms, so you can actually go from bulk to nano region. Again, the reason behind is that you can manipulate. So this, as I said, that one approach, after approach, you can create a new materials বা কোনো existing materials ke sizing, just changing the size, you can manipulate the properties, because properties is the most important. If you know the properties, because that properties actually are useful for applications. So surely again, any sensor or any applications, computer behavior. So it depends on the physical properties or chemical properties. Most of the cases, I think, depending on the applications. Okay, so surely if you are electronic applications, right? So that means electronic properties, particularly, or electrical properties, whether you can manipulate, or magnetic property if you are interested for magnetic random access memories or any other things. Then optics, right? Light or mechanical, or if you are looking for bio application, that means you need some material biocompatible as well as uh, biosensing kind of things. So surely this century actually, I believe is called nano bio info. These are the three areas are focused for these 21st centuries. So that's why a lot of people are working on that. And again, through nanostructuring, you can change, you can manipulate, you can engineer the physical as well as chemical properties. And that means if you can do that, then the question is you can think about how you can use it for applications. So surely, I think, again, this is from physics language, just like think about if you take a metal, any metals, a bulk material, metal. So always physics language deals with energies. So that means if you look at the energetics here, so it looks like, a discrete energy level, but it's almost continuous. But then when you, for atoms, you have a big separations. And then when you are nanoparticles, so you'll see that you'll have some kind of band, okay? So that means even through nano structuring, that means even for the gold, you can make it an insulator or semiconductor. Think about that. Surely, I think gold, all of you know that it's a metal, right? But one can make it even insulator or semiconductor through nanoparticles. So that means you can have the wide ranges of physical properties you can manipulate. Okay, so this is just a band diagram which can tell you, okay, this is the things you can do. And to visualize day-to-day life, right? That's why I think many people are really looking for called quantum dots. Again, quantum dot is not basically semiconductor, and you can change the band gap. Okay, so that means if you're again changing the size, previously I just talked about metal. So in this case, you'll see that when you are in the atomic, you have a band gap higher, close to atomic level. And then as you are doing quantum dots, right, so effectively your band gap is decreasing. And then effectively the materials, you can change the color, right? So that means, and again, this is a really huge application for semiconductor industry as well as biomedical application. That means the same materials, by changing the size, you can change the color. Think about that, right? So that means the optical properties. You look into that, how easy to make, red to blue colors, right? So that means you can have application in laser applications, or you can have again, as I said, biomedical application, drug delivery, tagging, all kind of things are there. So that's why the basically nanostructuring is very important. But there are many challenges we talk, because I think it's surely, it is just always people talk about the good thing, that okay, these are a lot of opportunities, but there are also a lot of challenges, right? So that's why the basically one has to work with that. Okay, how we can make a stable, because I think anywhere if you want to use for application, you need to have a stability, okay, and reproducibility, okay. All those things are important, okay. So surely, and again, this is just like I was talking about. This is the others result. This is just like whatever we made in our lab. Okay, different sizes of, say, for example, zinc oxide, and we look into the luminescence properties, particularly. So x-axis wavelength and y-axis intensity. So you'll see that means you can change that, how go from the luminescence properties, from bulk to the nano. Okay, so that means you can do that. So this is the actually utilize these properties has been utilized for glucose sensing and other things. And when you change this peak light intensity, one can use it for lasing application. So that means same material, zinc oxide, can be, for example, can be used it for drug delivery. It could be, biosensing, or it could be used it for lasing applications. And one of the thing, as I think next speaker, I think you talk, that is how it's possible that you can make these materials, anywhere in the world. In a sense, you don't need really big infrastructure. You can make it. You don't need a lot of funding for that. With a limited funding, you can make those. Okay, and then surely luminescence, optical properties, those are the things you can do it. But surely, if you want to make devices, that goes to high tech. That even, I think in US big universities they cannot make. Okay, so I think chemistry is beautiful in a sense. Through a lot of chemistry, you can create nanostructure. That is not a big deal. You can make it. So only thing is that, again, nanostructure could be in a powder form. It could be put into liquid, or it could be put on surfaces, depending on the applications. Okay, so we do most, both liquid phase as well as on surface. We can make those. So surely surface is a little bit more tougher, but liquid phase is much easier, and it's possible to do a lot of interesting stuff. Even, small colleges can do that. So surely, I think, as I said, the major applications, again, one of the things is that is called a lot of interesting, if you are a powder type, okay, liquid phase, right? So surely application is called drug delivery, okay? And then also it can be used for bioterrorism, for example, if you make it sensor, although this is a tougher job, no doubt, but the first one can make it. And then surely energy technology, we'll talk a little bit about that. And also, nanotechnology can be useful for information technology, because nanobio info, I think all these are interrelated. Okay, so that means everybody has to go to nano. So in that case, so surely for nanotechnology aspect, I think engineer, right, they will take care of it, or all the big labs, in a sense, I'll say that. So here, as I said, that I mean, mainly we'll focus major on for energy applications, particularly solar, because although always we are worried about energy, that energy cost goes up and all that things, but surely we convert one energy to another, right? But main thing, sometimes I say, okay, you don't have to worry about it because sun is there, right? This is outside the earth, right? So the idea is, say, can you utilize that energy, right? And you can convert it. So that means you have endless energy there, okay? And then you can convert that. So surely you need to have some technologies and how you can make it. So that means it's possible to have a clean energy. So I think solar energy is one of the cleanest energy. It's possible you can make it. And then the point is here, I'll talk about a little bit about that, how to make it, okay? So although it looks like you have a basically basic physics involved, some chemistry maybe required, and you'll see that you don't need a lot of, high-tech knowledge, but still I think you can make a solar cell and you can visualize, okay? But here, major idea, হচ্ছে যে how we can use the nanomaterial to enhance the solar activities. Okay. So surely, as I said, that energy, you have endless energy. So the day-to-day life, actually, all over the world, I think the electricity we use called 70 exajoules. Yeah, exajoules means I think it's 10 to the power 18. Okay, so now, so surely if you compare with the solar, you have a, 3 million, right? 850,000 exajoules. So that means you have endless energy. The only thing is that whatever you get it on the surface. So then the question is, how you can use that. Then surely you have other energies, wind and other things, and all over the world, again, trying to do utilizing the different form of energy, maybe wave energy, right, or sea wave and other things. People are thinking about that too. But here again, we'll focus on solar energy, okay? So, and then other is that, again, this is the mainly conventional energy, traditional, right? Any methane gas, right? Or gas, oil, or coal, you burn it and then, it gives you, you work on it, right? That's why the basically energy you get. But those are not actually carbon emissions are there, it's not clean, and also it will get over. So that's why people are looking called sustainable energy. That means it lasts a long time, does no harm, and leaves no changes. So surely, as long as sun is there, right, we are Earth is there, right. So that means whether you can utilize that energy, right, and also is a clean energy. That's why basically it's very useful. Apart from that, as I said, you might have other form of energy also sustainable, but I think solar, a lot of people are, all over the world, they are thinking about how you can increase the efficiency, how you can utilize it, and useful applications for that. So surely one of the applications, so for example, fuel cell, right? Here again, this I not talk, but this is a little bit away from solar cells. So in this case, basically you have endless water all over the earth, right? And then the point is you utilize the water, and if you can break the water through the sunlight, right, and then you can get basically the hydrogen, okay. So surely in that case, it can be used for hydrogen storage. This is another groups are, all over the world, people are trying to use the fuel cell, and how you can convert from water and sun energy, right, and then you can get it, okay. This is another approach, but again, I'm not talk about it. And again, for these actually, most of the cases, for example, here the example is called titanium oxide nanoparticles, because nanoparticles helps in splitting, the water into hydrogen and oxygen. So surely in this case, again, you need the absorption properties, which can break it, right, the sunlight. So that's why through nanostructuring, again, you can change the properties of the materials, and which can actually help to break the water into hydrogen and oxygen easily through the sun ray, okay, light. So that is another approach people are trying to do that. But as far as we say that this is easy, but I think main thing is that mastering, okay? So there are a lot of complexities are there. So that means one has to do the mastering of the complexity. So in that case, so surely a lot of things are happening. One have to understand the nanoscience, and then surely complex materials, computer modeling, all combinations, okay, and trying to see how the nanomaterials, right, can be utilized in our day-to-day life. So that means it is an endless opportunity. So surely if there is no lab, but still you can do modeling. A lot of modeling part these days is very easy, and you can do that. You can visualize. Still you can do a lot of good science. Okay, or simple, experiment. One can do it. It may not be great, but I think always from simple things you can do actually a lot of interesting stuff. Because I think if you get the experience, surely it will be helpful. Okay, so that means breakthrough to next generations. I think people are looking for sustainable energy technologies. So surely it is not there. People are looking for it. Okay. And so surely nano, you have actually a lot of another aspect, another groups are trying to utilize. We have also done a lot of works on how nano biointerface studies, because generally medicine particularly, nanoparticles are utilized for nanomedicine, for cancers and other things. And so surely in that case, if people want to use nanoparticle, nanomedicine, so surely one has to understand the nanobio interface, because nano generally most of the cases is inorganic, and then it is not basically one has to study the biocompatibility, how they interact. So these are one another aspect of science. So particularly the interface between biology and physics, okay, and maybe biology, physics, and chemistry. Very interesting areas in these research areas. Okay. So now here, that whatever I showed you my lab, right? So in that lab, right? So effectively, we can create all kind of nanostructures. Okay, so surely, you know, this is basically trying to give you the just a flavor of zinc oxide. So effectively, again, depending on the surface. So this is not on a surface; it's just a particle, but these are on a surface. So that means you can make it, okay, on a surface of the nanoparticles. We can talk a little bit, but uh, we'll see later on. Okay, but surely whenever you have it, okay, so there that means you surely, I think these days maybe not possible to have all the technologies, characterization techniques, but as far as I understand, India, a lot of collaboration is going on. So that means you have a research center. So that means key thing is that materials, if you can make good materials, okay, and then if you have some basic characterization so that you can do something, and then other characterizations, actually, you can do it through collaboration. I think that will surely be helpful. Okay, so surely, for example, IIT Kharagpur or many other places, you'll see that. Okay, and there, I think you'll be able to do a lot of work. Okay, so now maybe I'll come into that basic science, that how to do the solar to electric energy conversion. Okay, so first thing is that maybe you know that charge separation. So for example, in any battery, for example, lead acid battery. So if you can separate the charge between two electrodes, right? So that means one will have more charges, another will have less charges, right? So in that case, you are basically creating a potential. That is the basic principle. So here, what you are converting the chemical energy into the electrical energy, but main thing you are separating the charges. So same thing uh, through the light, actually your goal will be to separate the charges. Okay, that's why we'll talk about that, how you can separate the charges between two electrodes. And if you can separate the two charges through the light, then actually you have the battery. Okay, you have the solar battery. Okay, that is basically the way. Okay, I think for physics point of view, I think if you surely you need a semiconductor, right? You have to call the bottom one is called band diagram, right? Valence band and conduction band. So when the light falls into that, the idea is that basically electron goes from here and basically goes to the excited state. Okay, so now actual, the previous one is just I was showing that, but here in this case, actually the band is looking like these. Okay, so most of the cases the electron goes from the valence band to conduction band, but it actually come back. Okay, so that means absorption, but at the same time you see the emission. Okay, so then the question is, main thing is that you are throwing this electron, but you need to take that electron out. Okay, separate it. Okay, if you can collect that electron the way, so then you have the solar cell. So this is just a light in any materials. Actually, if you any semiconductor, if you have photon is coming, it will go from valence band to conduction band, but then it will come back. But your goal will be this red ball, right? The electrons you need to separate. That how do you do that? That is called actually the called device, the solar cell. Okay. So think about, as I said, that for the solar cell means if you have a two electrode, electrode one and electrode two, so you want that electron going from here to the left to right. And how do you do that? Okay. So for that, actually, at
Uh,
least you need.
I just disturbing you, the Dr. Host. Your
Yes.
present screen is some switch up, so please try the present screen also.
Which screen? Uh,
That because someone is start the present screen, that's why your present screen is switch off. So please
okay,
start
let
again.
me stop sharing and again share, right?
Oh yes, yes,
Okay,
yes.
stop
So Devashish
sharing.
Bhaskar, please switch off your present screens. You are most of the time present your screen.
Oh, okay,
When you
sure, sure. Let me try that. Okay. Uh, okay, okay. So present now. Let me see that. Present enter screen. Are you seeing that? My screen?
no, 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 I'm not.
How about now?
Yes, it's starting.
Oh, okay. So slide. So current slide. Can you see now?
Yes, yes.
Okay. So did you see the previous slide or not? I am not sure. Okay. Uh, anyway, so the idea here is that you have a electrode 1 and electrode 2, right? So you want to separate the electrodes, okay? Trying to get some electrons from one electrode and transferring to others, okay? How do you do that? Okay, so that means you have the electron here and you have electron here. Surely what function will be different, okay? So now when the light comes, right? So electron goes here and then come back here and then come back here, okay? So, but then the point is, so that means you need certain materials you have to call band alignment. You have to do that in such a way. That means you need at least 4 materials, okay? Electrode 1, electrode 2, and then you have a 2 materials, okay? So basically you will have a 2 materials where you will create a junction, okay? It's called PN junction, okay? And then effectively you'll be able to transfer the electron from one to others. So if you can do that, so that means you have the solar cell. That means you have two things. One is the absorption, one is the separating the charge. Okay, so that means before it come down, you are basically taking the electron to the other electrons. Okay, so this is basically the main thing of the solar cell. So here, this is the main structure in a sense. If you look at that effectively, you have a semiconductor 1, 2, and then you have a top electrode, bottom electrode, right? And then the light is coming and electron is going. And so that means you will get the light here, okay? So that basically give you a very basic of that. And then the point is, how do you know that how good battery it is, right? So that means how good cell is. So then only thing is that very simple thing that is called IV curve, just like a multimeter use that just like you measure resistance, but not exactly here. That effectively is called IV curve. Okay, IV curve is a key for all electronic industries. Okay, so that means you'll be if you can do the IV curve, you will be really, really way ahead. And it is actually possible anywhere. Okay, if you have a small college, still I think if you have a current meter, you have a voltmeter, you can do that. Okay. So surely if you can do the IV curve, and particularly the main thing is called dark, this is called diode characteristics without light, and then this is called with the light. So that means this is the basically called power you'll be generating this fourth coordinate, okay? So whatever the, difference between dark and light, whatever you get, actually that will give you basically the power consumption there, okay? So anyway, then surely we'll talk a little bit our research, but then the point is again, as I said, you have to have. Also, it's possible, as I said, that there's a nice software. It's called SCAP. Effectively, if you are interested for solar cell, you can actually even do some simulations, and you can publish good paper out of that. For example, this is just like a 2020, computational material science. Effectively, through just you can visualize that. So effectively, you have, as I said, you have a in this case you have a 5 materials and one can create that solar cell. Okay, that means you can get the idea about how it will behave, okay, before you make it, because making is a little bit tougher because you have 5 layers, right? It will be tougher, but It's possible, I'm not saying that it's not, but you can actually, one can visualize that. So sometimes we actually always, before doing the experiment, maybe we simulate that how is it possible, okay? So that means you need a two electrodes here, and then you have a three materials or two materials, and then you can just calculate, or you can find out your IV curve, and from there efficiencies and everything you can calculate, okay? So surely one of the thing is that main thing is that you have to again all the materials properties you have to know. Okay, so surely you can get the materials properties from the literature, or if you make your new materials, surely you have to find out the parameters. Okay, so this is the things you are looking for. Okay, this is just a giving you example that okay, even if you don't have any lab experiments, still you can do a lot of simulations. You can understand, visualize the solar cell. And this is just giving you that you can really generate nice data out of that. But although there's a big difference, but at least you will be able to visualize, you can start doing some experiment from there. Okay. But in our case, what we did actually here, the idea is effectively, this is the again called band alignment, the separation, right? You have one electrode, you have another electrode. One is called RGO, another is called aluminum, okay? And then, so surely again, you can have two or three. So in this case, we have a zinc oxide, copper oxide, and then we have a mixture of that. And then also some organic layer if you want. And sometimes we make some nano rod also because it gives you more diode characteristics and it can increase the efficiency. This is basically giving you a schematic of that. Okay. So, but key point here is that, as I said, that materials, materials, and materials. So effectively, a couple of things for any solar cell, you need one layer is called transparent conducting layer. Okay, so it has to be transparent as well as conducting. Okay, so this is a one of the group people are trying to do research for transparent conducting oxide, and particularly people are trying to do called on flexible substrate. And these actually, these transparent conducting layer actually, even you can make it at any college level, people can do it. Okay, so in that case, only thing you will be doing that, whether it is transparent, that means simple light experiment and simple IV measurement, one can actually make it on just a transparency sheet, for example plastic sheet, people can make it. Okay, so surely, although here we are trying to use the graphene you can buy it very cheap, you can get it, or you can make the graphene powders. Okay, and then surely graphene powder with some other composite. People are trying on developing called transparent conducting materials. Okay, so in our cell phone to touch screen, everywhere you need that. Okay, wherever you need the capacitance, you need actually transparent material. So this is actually we are also developing in one of the aspect here. Okay, so then surely in many cases helpful. This is a little bit high level that in a sense called nano rod. Okay, so nano rod, so surely we grow using PLD. We can do that. So this is just giving you example here. So then organic coating sometimes, and then nanoparticles. This is the way you can do it. But I'll be skipping that. But main thing here. Now let me summarize. One of the thing is that main thing always you have to think about growth of materials. Growth of materials on surfaces. If you are trying to make some solar cell or electronic device, field effect transistors or semiconductor device. Okay, so and then main thing is that it has a many aspect. Okay, so first thing is that you make the materials right, and then the point is you try to study the structure. So X-ray, electron microscope, AFM, or electrical properties, magnetic properties, optical properties. Again, you don't have to do everything, but at least if you can do one characterizations, that itself will be helpful, because then other people will be able to actually ready to collaborate. Because if you can make the materials and so okay, I got some interesting properties from one characterizations, okay, then maybe other people will be very interested to do that. Okay, but surely that again you have to go back and forth to optimizing the materials. Is not just like that. Any materials you make it, you have to call optimization. A lot of big processes there, but that's why the basically undergraduate students can do it. Okay, so here I'm just talking a little bit about simple technique. Okay, is called hydrothermal, where you can create actually the nanomaterials in a different form, from nanoparticles to nanorod. Okay, so these basically, again, these I got it from India. Okay, is only 500. $500 means 35,000 rupees a couple of years back. Okay, but I'm sure if you want to buy from there, it will maybe $10,000 to $20,000. So you have basically the synthesizing technique. Okay, you can create the nanomaterials starting from a lot of nanomaterials. You can do it. Okay, basically it's called a hydrothermal, just meaning you have a water and then temperature and then pressure, and you can create really lot of varieties of nanomaterials. Okay, this is the one way. Okay, and then other is simple chemical technique. You can do it. Okay, so then surely this is the technique what we use a regular if you want to do on a surface, right? So then this technique is name is called PLD. It's called pulse laser deposition. Okay, so basic principle is simple. You have a laser which is a pulse laser, nanosecond laser, but you burn just like burning a paper using a sunlight. So basically, you focus the laser beam in a basically control. These two called chamber is called control atmosphere. Okay, because you have to have a control ways of doing it. Okay, so that means it does not. You don't want to react with the air or other things, right? So, but main basic principle, just like a lens, mirror, and you need some laser. Okay, so and then you can actually create a lot of materials. Any materials you want, actually you can create on a surface. Okay, although we focused on oxides. Okay, so this is just giving you ideas here. You know, even you can start with simple things. Okay, so although this is a little bit hi-fi laser, but it's not necessarily you need the hi-fi laser all the time. Okay. Okay, so this is basically, again, that basically just giving you the basic principle. Lens, as I said, lens, mirror, and you have the excimer laser. That means if you know the equation of the lens, you know the reflection of the mirror, reflection by a mirror, and then you can focus the laser beam and you can create a temperature like 5,000 degrees Celsius, okay? And for a nanosecond, which can give you basically called plasma, and then you can make the material. So any materials you want, okay, is gold, tungsten, composite, any materials you want, actually you can do it. Okay, and also the idea is, as I said, control atmosphere. That means you can use a different reactive gases. So this, I believe, just like a materials is nothing but a called cooking. So that means if you have a proper ingredient and you know how to cook, right? Procedure, okay, you can actually have your own. So that means what you need, you need the energy, right? For cooking, you need the energy and you need the ingredient. Then you can have a good. So same thing actually, you can have a good materials, okay? So and actually that is the key for success, okay? Anything you want is for that, okay? So that's why we are actually trying a lot of varieties of things. Graphene, starting from graphenes to gold, okay? So anything you can make it using this technique. Okay, so surely then again, we do the characterizations, right? All kind. I think I have already shown you, right? Basically, first thing you need to look at the structure. So effectively, we do through X-ray diffractions, or electron microscope, or optical techniques. Okay, this I'm just giving you a little bit idea that how good materials, whatever the materials you want it, whether you got it or not. Okay, I think that is the key things you need to look into that. Okay, so now maybe one of the interesting things is, I think is a good point to look into the called fabrication of a solar cell. Okay, how do you take it? Okay, although you think that is difficult, but if you have even a paintbrush, you can do it. Okay, you don't need the laser. Okay, so now think about, you take a glass slide. Okay, just like transparent glass slide, you take it. Okay, and then what you do, you basically try to, is called masking. Okay, so that means for example, you can put your conducting materials here just like a painted. You can paint it like this, okay? Or if you have a more sophisticated, we can have like this, just like effectively you have the materials here, okay? Then you have basically, this is my one electrode. If you do remember that I need a 4 or 5 materials. So this is the one material, the first layer, okay? This first layer, okay? And then second layer, basically, that's called mask. That means basically I make my ITO or transparent conducting oxides. Okay, and then effectively you coat it your zinc oxide layer. It could be PLD or it could be spin coated or it could be paint brush. You can put it like
তুমি
this.
যা
Okay,
করছো করো না।
and then when you have one
না
layer
এখন হবে
like
না,
one semiconductor, then you put the another semiconductor.
পরে দিও না।
Entire p-type, and then if you want to put other
দিবি তো?
layer, organic layer is not necessary. Organic layer means you put a solution, you put it on that, and then you basically try to just a cross of these. Okay, if you have a cross of that, so effectively in this case you will have a call the top electrode gold or silver or something like that. So effectively you grow that. Okay, so in that way the each junction actually gives you one battery, one cell. Okay, so that means in this case you have a 25 cell. Okay, so effectively this is the way actually again you can have a sophisticated one, but if you want by your hand, actually you can make it. Okay, so this is 25 cells, so this is not a big deal. So but again, this for a college student, right, you just try to use your own innovative ideas and you can do it. Actually you can do it, one can do it just like simple ways you can make it. Okay, not only that, if you want to really find out, a lot of YouTube these days are available, you can look into that. You'll find that any lab actually with a limited budget you can make the solar cell. Okay, so this is basically give you, and then again this is most of the, in our cases we try to collect the data through that. So here again I already go through that. So main thing, we characterize it different ways, right? Depending on that X-ray, Raman, PL. Again, I'm not going through those details because I already talked about that. So these are again properties of various materials. I'll also cross these because we'll have a time limited, but again, don't worry too much here. This is basically called analysis of the data, Raman, XRD, right? How each layer, right? Basically, each layer, when we make it, each layer we try to characterize using X-ray diffraction, Raman spectroscopy, and all that. But main thing, most important one is called absorption, which actually is possible by any lab. You need basically a simple spectrometer, couple of minutes, right? I have it. Okay, let me see. Okay, so I'll try to finish in maybe 5 minutes. Okay, so here the idea is called, transmittance. Okay, so effectively we created different varieties of nanostructure. Think about that. Okay, and then we found for a specific nanostructure the absorption is huge, even better than silicon. Okay, so then basically that's why we try to make the solar cell using all these materials, and then we see what we get. Okay, so surely if you really go back to the history, copper oxide is the oldest first solar cell, and that efficiency was 0.01%. So we started with that, and then we nanostructure and we show that your efficiency goes up. Okay, so surely again we try to understand that how the different structure comes. So this is basically again mechanism of the nanostructure, why sometimes it forms like that, sometimes it forms like that. It's a little bit hand wavy mechanism. We have it little bit called chemistry and ways. Okay, so then surely we need to do, if you want to do any, good solar cell, is good to know about the, surface. If surface smooth, it will be better. So that's why we do sometimes AFM on that. Okay, and this is the key in a sense, is called solar cell. Okay, so the IV characteristics. Okay, so surely if you look at the IV characteristics, as I say, light, no light. So these basically gives you a different materials, different, bulk materials and nanomaterials, and specifically that nanomaterials which shows high absorption, which is the first thing. If you want for solar cell, you need that. Okay, so in that case, so that means what you got it here, if you look at that here, if you look at into the table, we started with that, ITO, zinc oxide, copper oxide, just thin film. It's basically bulk kind of things. You have a basically 0.03%, which is nothing. But if you do the nanostructure, specific nanostructure, we got 3%. So surely if you really look into that 100% increase, okay? So that is basically surely that 3% is not a big deal because 3% is nothing. But from the science point of view, what I'm trying to say that, right, the nanostructuring helps huge. So that means this is the concept one can do it. Okay, that how you can improve the efficiency. This is just an example here, right? So you can do many other ways of nanostructuring, and you can get how you can get there. So let me summarize. So effectively, again, I was trying to give you that, okay, the nanostructures, that how you can create the nanostructure by varying process parameter. Okay, so process parameter here, as I say that, just like a chemistry or laser ablation, right? So effectively, I think everywhere you need the energy, okay, energy, and then the materials, proper materials, okay. So that basically you can vary the nanostructure through that. Okay, you can create a different materials. You can create, for example, same methane gas. You can use a diamond or graphene. Okay, but depending on the energetics, you can change that. Okay, so here the same thing. Depending on the energetics, you can create the different materials. I think that is the key things. Okay, so now you can do it through the chemistry, chemical routes, hydrothermal, or PLD, CVD, many ways you can do it. But I think everybody can do the research if you have the intention. Let me tell you that. Okay. So surely, again, here I have just shown you one specific example, particularly copper oxide nanostructure. We showed that you have for specific nanostructure, it gives you a huge absorptions. And so surely using that materials, because that's the first criteria, but also it's a semiconductor, we showed that solar activities can be highly enhanced. Okay. So surely again, whatever you do, right, I think good thing is that understanding, okay, understanding the properties of the nanostructure, and I think surely it will help in designing many unique new devices for future devices. Okay, so here are some just some of my students. Again, thank you. uh, uh, Acknowledge to others, right, students, postdocs, and also funding agencies here. Thank you, and surely I'll open for questions here.
Okay, so if any participant have any question, please ask. And Dr. I have one question. Some people are seeing our YouTube live channel. So Rajesh Mukherjee has want to know some question. So what is the software for simulation this solar cell data?
Okay, so yeah, SCAP, SCAP, okay. Okay, I think it's a free software. It's a very useful. Okay, I'll tell you that people really publish paper. You don't need anything. Okay, so only thing surely you need your intellectual level, right? You have to work on it. Okay, so surely a SCAP. Let me tell you, SCAP. Okay, you search it, and or you can send me an email. Okay, maybe I'll send you the link. Okay, and it's a free software. You can get it. Okay, it is basically developed by Denmark somewhere. We also use it. Many people uses it. So surely, I think you'll really, whenever you do it, you'll feel really good on that. Okay.
Okay. So if anyone else have any questions?
বাংলায় কোশ্চেন করতে পারে। আমি অ্যাকচুয়ালি ফার্স্টে ভাবলাম বাংলায় বলবো, কিন্তু সবাই দেখি ইংলিশে বলছে, তো হ্যাঁ, কোনো অসুবিধা নেই।
তো যদি কারোর কিছু প্রশ্ন থাকে একটু করতে পারেন, স্যার এখনো আছেন এবং অ্যানসার হয়তো দিয়ে দেবেন।
হ্যালো,
শিওর।
হ্যালো,
হ্যাঁ বলুন।
আমি একটা প্রশ্ন করছি। এখন কি কোনো ন্যানোমেটেরিয়ালের সঙ্গে এখন যে করোনা ভাইরাসের কোনো কাজ, রিসার্চ ওয়ার্ক হচ্ছে?
হ্যাঁ, অ্যাকচুয়ালি হচ্ছে, ইভেন আমরাও করছি। শোনো, হ্যাঁ, ওকে, করোনা ভাইরাস তো বিভিন্ন অ্যাসপেক্ট আছে, রাইট? বিভিন্ন অ্যাসপেক্ট আছে, পিপল আর ওয়ার্কিং অন দ্যাট। কিন্তু এখন যেটা আমরা একটা ছোট্ট কাজ করছি যদিও, হ্যাঁ, এটা হচ্ছে আমরা পিপিই, ওকে, হ্যাঁ, that how to kill the coronavirus externally, okay, I think that is the key. মানে আমার যেটা থিওরি আছে যে এখানে যে you can kill the virus most of the cases, মানে মানে পিপিই যারা আমরা ফেস মাস্কটা ইউজ করি, ফেস মাস্কে স্পেসিফিক কোটিং দিলে সেটা করোনা ভাইরাস ক্যান নট করোনা, এনি ভাইরাস ক্যান বি কিল, করোনা ভাইরাস নাথিং বাট ভাইরাস। Surely nanostructuring people are doing research.
Is there any কোনো modeling work করা হচ্ছে?
মডেলিং ওয়ার্ক করোনা ভাইরাস নিয়ে তো এটা তো স্ট্যাটিস্টিক্যাল মেকানিক্স নিয়ে ইয়ে করছে বেশিরভাগই। আমার মনে হয় না সিওরি ওটা সম্বন্ধে খুব একটা জানি না, কিছু পেপার দেখেছি, ইভেন টিআইএফ একটা গ্রুপ পাবলিশ করে মডেলিং নিয়ে যে কিভাবে কি হবে, মানে যদি ফেস মাস্ক ইউজ মানে লকডাউন হবে, লকডাউন হবে না, তার উপরে বিভিন্ন। কিন্তু আমার মনে হয় না সিওরি, মানে অতটা আমি জানি না, কিন্তু ফেস মাস্কের উপরে আমরা কাজ করছি জানি, এবং অন্য লোকজন কাজ করছে, কারণ করোনা যে কোনো ভাইরাস ইজ তো মেড অফ প্রোটিন, রাইট? এটা হচ্ছে স্পেসিফিক্যালি পাইক প্রোটিন, লিপিড লেয়ার এবং আরএনএ, এই তিনটে লেয়ার, রাইট? এই তিনটের মধ্যে ইন্টারাকশন, রাইট? এই তিনটে নিয়ে মেনি পিপল আর স্টাডিং, হ্যাঁ, লট অফ পিপল আর স্টাডিং অন দ্যাট। তো অর্থাৎ এটা একদিনের রিসার্চ ইজ নট একদিনের রিসার্চ, তো আমার মনে হয় আজকে শুরু করছে না, অনেক লোক করছে এবং প্যারালালি আরো লোক করছে।
ক্রিস্টালোগ্রাফিতেও এক্সরে ক্রিস্টালোগ্রাফি
হ্যাঁ, শুনতে পাচ্ছি না। হ্যাঁ,
যে যে এক্সরে ক্রিস্টালোগ্রাফি
এক্সরে ক্রিস্টালোগ্রাফি
কিছু ড্রাগ ডেলিভারির কাজ হচ্ছে, অর্থাৎ intercalation or something else, particular target design.
না, এক্সরে ডিফ্রাকশন নির্ভর করছে এক্সরে ডিফ্রাকশনের রেজলিউশনের উপরে, কিন্তু বেসিক যে কোনো লোকই করতে পারে বেসিক এক্সরে ডিফ্রাকশনস, রাইট? তো এক্সরে ডিফ্রাকশন ইজ দ্য কি, মানে যে কোনো মেটেরিয়ালস এর, মানে particularly nanomaterials are very useful for characterizing X-ray diffractions.
Okay, thank you.
Sure. হ্যাঁ, মানে কেউ মানে আমি অখুশি কোনো কিছু হব না, বাংলায় কোশ্চেন করলেও কোনো ব্যাপার নেই। আমি ভাবছিলাম বাংলাতেই হয়তো দেবো, কিন্তু তারপরে বুঝলাম মানে সবই তো ইংলিশে ইয়ে আছে, কিন্তু যদি অসুবিধা হয় নিশ্চয়ই বাংলাতে ইয়ে করতে পারো। হ্যাঁ, আর কোনো কোশ্চেন থাকলে নিশ্চয়ই আমার ইমেলে কোশ্চেন থ্রো করতে পারো, এবং কোনো কোলাবোরেশন এনিথিং, মানে যদি কোনোভাবে হেল্প করা যেতে পারে নিশ্চয়ই আমি আছি।
চ্যাট বক্সে আর একটা দুটো কোশ্চেন এসেছে, তো
শিওর।
অমিত কুমার দুনিয়ার is it possible to tune the lattice constant in the nanoscale without changing the nature of unit cell?
ল্যাটিস কনস্ট্যান্ট, সারফেসের ল্যাটিস কনস্ট্যান্ট চেঞ্জ হবে বেশি। হ্যাঁ, এটা যদি আমি ধরি একটা ন্যানো পার্টিকেলস নিই, রাইট? ইউ হ্যাভ এ কোর অ্যান্ড মেন কোর অ্যান্ড সারফেস, রাইট? কোরের ল্যাটিস কনস্ট্যান্ট খুব একটা চেঞ্জ করা ডিফিকাল্ট আছে। হ্যাঁ, মেজর হচ্ছে যে সারফেস এফেক্ট, রাইট? মানে ন্যানো পার্টিকেলস এর মেজর ইস্যুটাই হচ্ছে সারফেস এফেক্ট। সিওরলি সারফেসে ল্যাটিস প্যারামিটার ইজিলি চেঞ্জ করা যাবে। হ্যাঁ।
There is another more question from the YouTube link. What is the size of the QO of the good solar activity?
What is the
Size of copper oxide for the good solar activity?
what is the size? Okay, আমরা সোলার অ্যাক্টিভিটি, মানে এটা একটা জাস্ট একটা এক্সাম্পল আমরা দেখিয়েছি। হ্যাঁ, এবং পার্টিকুলারলি শেপ এবং সাইজ দুটোর উপরেই নির্ভর করছে ফিজিক্যাল প্রপার্টিসটা, রাইট? ওকে, আমাদের সাইজগুলো খুব একটা ছোট্ট ছিল না, এটা ছিল অ্যাবাউট 20 ন্যানোমিটার্স। ওকে, তো জাস্ট মানে যত সাইজ ছোট হবে তখন সারফেস এফেক্টটা মোর প্রমিনেন্ট হবে। হ্যাঁ, কিন্তু সেইখানে আবার প্রমিনেন্ট হলেও তখন দেখতে হবে মানে ডিফেক্টও বেড়ে যাবে, অর্থাৎ মানে লট অফ ইম্পর্টেন্ট থিংস আর দেয়ার, মানে সোলার অ্যাক্টিভিটিস অনেকগুলো প্যারামিটারের উপরে নির্ভর করে, তার মানে অপটিমাইজেশনস আর নিডেড। ওকে, ইটস নট জাস্ট লাইক ওয়ান, মানে ছোট করলেই যে অ্যাক্টিভিটি বাড়বে তা না, ইউ নিড এ অপটিমাল প্যারামিটার। হ্যাঁ, আমরা অতটা এখনো অপটিমাইজ করি নাই। হ্যাঁ, জাস্ট একটা আইডিয়া দেখিয়েছি যে হ্যাঁ মানে ন্যানো স্ট্রাকচারিং ক্যান হেল্প ফর দ্য টু improve the solar activities.
Another question is, have you used any nanoparticle in the fiber optics?
No, not really. In fiber optics particularly আমার মনে হয় যেটা ফাইবার অপটিক্স কেবলে যেটা ডাইলেকট্রিক কনস্ট্যান্ট দরকার, তাই না? হাই ডাইলেকট্রিক কনস্ট্যান্ট মেটেরিয়ালস আর নিডেড। হ্যাঁ, আমার ওইটার সম্বন্ধে আমার কোনো আইডিয়া নেই। হ্যাঁ, ইটস পসিবল, কিন্তু মানে হাই রিফ্লেকটিভ ইন্ডেক্স মেটেরিয়ালস নিডেড। হ্যাঁ, রিফ্লেকটিভ ইন্ডেক্স চেঞ্জ করতে পারলে নিঃসন্দেহ হবে হয়তো।
And the last question is, why the perovskite solar cell gaining the more attention in the nowadays?
No, solar cell পেরোক্সাইড হচ্ছে বেসিক্যালি, এটা হচ্ছে মেন হচ্ছে যে অর্গানিক ইনঅর্গানিক, এটা হচ্ছে একটা কম্বিনেশন মেটেরিয়াল, যেটা সোলার সেলটা শুরু হচ্ছে অর্গানিক ইনঅর্গানিক। হ্যাঁ, এবং মেন হচ্ছে যে যখনই সোলার সেলের ওই মেটেরিয়ালস এর স্পেসিফিক প্রপার্টিস, পার্টিকুলারলি তুমি যদি ওই একটা মডেল দেখালাম যে ইলেকট্রন ইজ জাম্পিং রাইট অ্যান্ড মোস্টলি ফলিং ডাউন, তাই না? ওই জিনিসটা হচ্ছে ওইখানে ওইটাকে বলে মেটাস্টেবল স্টেট। ওই স্টেটে যদি বেশিক্ষণ রাখা যায়, দ্যাট মিনস ইউ আর অ্যালাউইং লং টাইম টু কালেক্ট দ্য ইলেকট্রন। হ্যাঁ, মানে সোলার সেলের বেসিক প্রিন্সিপালটা হচ্ছে লাইট অ্যাবজর্ব। The electron is, you are basically getting the electron, right, jumping it, and then basically that is used to transfer the electron from left to right, one electron to other electron, কিন্তু ওই ইলেকট্রনটাকে একটা মেটাস্টেবল স্টেটে থাকতে হবে। কিন্তু এই পেরোক্সাইড মেটেরিয়ালস এর যে ব্যান্ড ডায়াগ্রাম থেকে দেখা গেছে যে ওটা মেটাস্টেবল স্টেটটা বেশি ভালো, সেই জন্য ওইখানে স্টেডি থাকে। তো এবং তারপরে তার এফিসিয়েন্সিটা অনেক বেশি। কিন্তু there are a lot of challenges because organic and organic is not stable at all. Okay, so a lot of people are doing research, but finally getting for real application is a tough.
So another question is, what about the plasmonic solar cell?
Huh?
What is the plasmonic solar cell?
Plasmonic মানে ওইখানে ওই again your idea is to, you are creating some, মানে not wasting the light. Okay, so basically some kind of light harvesting in a sense. So effectively you, whatever emissions you get it, plasmonic emission, and then effectively you try to utilize for absorbing. Okay, so main thing is that your efficiency, right? So how you can increase the efficiency through absorbing more light. Most of the light you are trying to utilize it, not losing it. Okay, তো তারপরে কিছু গ্রুপ ওই প্লাজমনিক করে ইউটিলাইজ করে, যে কোনো তুমি দিচ্ছ যখন তো একটা লুমিনেসেন্স তৈরি হয়, রাইট, এক্সট্রা লাইট তৈরি হয়, সেই লাইটটাকে আবার ইউটিলাইজ করা।
So another question is, perovskite, copper oxide perovskite is showing the low efficiency. So why are you using these types of perovskite, and what is the causes for copper oxide getting the low efficiency?
না, এগুলো হচ্ছে জাস্ট আমরা বোঝার জন্য করছি। হ্যাঁ, পার্টিকুলারলি দেখো মেন পার্ট হচ্ছে আমাদের গোল হচ্ছে নট এক্স্যাক্টলি টু, মানে খুব বেশি পেলে ভালো, বেশি পাওয়াটা যে খারাপ না তা নয়, মেন হচ্ছে যে আন্ডারস্ট্যান্ডিং দ্য সোলার অ্যাক্টিভিটিস। মানে কপার অক্সাইড নিয়ে বেটার হয় না যে টাইটেনিয়াম অক্সাইড বিভিন্ন, যেহেতু আমরা অক্সাইড নিয়ে কাজ করি, মেনলি হচ্ছে আমরা আমাদের মানে স্ট্রং পয়েন্ট হচ্ছে আমরা অক্সাইড নিয়ে কাজ করি, কপার অক্সাইড, জিঙ্ক অক্সাইড, টাইটেনিয়াম অক্সাইড, বিকজ PL is very good to create that materials. Okay, and then the point is আমরা যেটা ভাবছি যে আমরা চেঞ্জ করতে পারি, যদি স্ট্রাকচারটা চেঞ্জ করতে পারি, ন্যানো স্ট্রাকচারিং, whether that can help, এবং সেই কনসেপ্টটা যদি অন্য জায়গায় কোনো কাজে লাগানো হয়।
So now thank you to Dr. Bose for presenting here a very nice presentation regarding the recent trends in the nano device and the nanomaterials. So thank you again, and thank you all participants also for being the peaceful having this meeting. Now our
Thank you all. Okay, thank you all.
next talk will be delivered by Dr. Samaresh Das. He's one of my senior in the IIT. I have teach many more things from him. So now, Dr. Das, start your lecture and present your valuable presentation.
Hello, can you hear me?
Yes, I am getting your voice.
So can you see my screen? Is visible?
I am not. I am seeing your face. So
Because it is showing a presenting now. Can you see now?
no.
But in my computer it is showing the presenting now. Okay. Can you see now? Hello?
Hello. I'm not getting your screen. I have just seen your face and your webcam is working.
But I share my, because Meet tool is sharing a window. I share my PPT.
Just in the Google Meet, start the presence.
That's what I'm doing. Like, are you able to see?
No.
I don't know. Otherwise, I can send you the PPT. You can show. There is some error. I don't know when screen sharing.
So you just restart your Google Meet again.
Hello.
Hello. Yes, it is starting. It is working.
Okay. Thanks. Now it is showing.
It is showing.
Okay. Okay. I think it is visible now.
Yes, it is visible now.
Okay, first I'm very thankful to Professor Montu Das. Actually, I had a good memory in Minnapur, so I started my career at Minnapur College, actually, where I did my BSc, and I did mostly learn lot of things from Dr. Montudas, and so I'm very thankful that time also, this time, like, for giving this opportunity. So I'll be mainly presenting the device aspect of this nanomaterials. So not much about the materials things. So my group, like I'm in the Center for Applied Research in Electronics. So my research area is mainly the application of these nanomaterials, mainly semiconductor nanostructure. So this is the group research interest. So I work mainly the photo detectors from visible to infrared detectors development, and we have started the activity on terahertz electronics. I'll explain a little bit that, because that is the emerging technology, and also quantum electronics. We have started working, and also some students will collaborate with the biotechnology department. We work on the biosensors, mostly field effect transistor based biosensor. Okay, so this is the research facility in my group. So we have the full device fabrication facility along with the device testing, like electrical as well as the optical. Like only we make the, as I discussed, I made the device, and then by mainly the physical vapor deposition, but with some students started on chemical synthesis also, because that is, but for the device point of view, we want very scalable approach. That's why we prefer the physical vapor deposition or top-down approach. So I'll little bit discuss on that. So this is the outline of my today's talk. First, I will discuss what we are standing in the electronic and optoelectronics perspective, and then little bit on semiconductor nanostructure, although it has been discussed by the previous speakers, professor. So I will mostly then some of the optoelectronics devices which we are working, and then summary I will discuss what you can do, like for the faculty as well as for the student in the future. So we'll discuss two aspects. One is for the faculty research scholar, and those students who are doing the BSc, then what is their, like what they can go after BSc. So if you see the electronics evolution, now all of you have the mobile phone and all these things. So you already have 10 nanometer technology node. So, and it is not like the planar MOSFET, it's already come to the FinFET. If you go, maybe it will be difficult to understand the FinFET technology. But if you see the technology node, so now it is coming to around 7 nanometer technology node. Like TSMC are going to launch this 7 nanometer this year, and also Intel is also trying to 7 nanometer technology node. But if you see like the Samsung Note Plus of these things, they already have 10 nanometer technology node. So there is not much work you can do for the like the transistor development. So you have to find out some other application of this transistor. So derivation application, it is not like the only the switching application, and you can do a lot of things on the circuit side also. And if you see the evolution of the electronics, as I discussed in the mobile phone, and also the now coming is the electronic car, where all the different types of sensor, like from the control systems, you have the discrete control systems, where you have the field effect transistor based control system, like APT based control system, and for the sensor surrounding, you have the Wi-Fi sensors, and also for the different types of sensor, there have a MEMS technology, electromechanical system. So there is a lot of sensor, and for the radar technology, because your car also like driverless cars or anything, so you need a radar. Radars means which will emit the signal and it can receive also the signal, so that you need high pass and high data rate radar also. So people now using mostly silicon germanium or hybrid technology for this radar technology. And for the power devices, because in the car you need a lot of power control, so that also needed like gallium nitride based technology power, because silicon cannot handle that much power, but the control system is still silicon. And for the infrared imaging, like in the night vision camera, all these things, even in the car you have the gallium arsenide or silicon germanium based photodiode, and also other things like as I told, like for the Wi-Fi you have the is silicon or insulator technology or gallium arsenide technology. So and after the silicon, what we can do? So there is a a lot of work is going on throughout world for the development of quantum computer. So the basic things for the quantum computer is the first you have to develop the quantum bit. So there is a lot of approaches going on for the development of the qubit. So there is a like I am from the semiconductor side. We are mostly thinking about the charge or spin qubit. So like the for the normal transistor you have a on state or off state, whereas in the quantum bit like you can take a single atom. So like you have a single atoms, like this is the single donor atom inside a transistor. Like you have only one phosphorus atom inside this transistor below the gate. So this donor atom can act as a single atoms. They have different energy levels, and you can control this state, like where your electron is going on the fast ground state or fast excited state, and you can make the superposition of this ground state and fast excited state, and you can make the control of that thing. So you can make the in a quantum bit, you can make any superposition of this state. And if you represent this around the sphere, like for a normal transistor, you have a on-off states, two states. But if you have a qubit, like you can think about this sphere, wherever you can put the point, that state you can create. But you have to need control like gate operation. So these are the challenge. Like how can I put the like one state like 0 state or 1 state or anywhere in the superposition around this sphere. So you need a gate control of that things, and that is the super challenging, how to control that things. And you can control not only the like a single atom, you can control the single electron also. Like if you confine a single electrons, it can have a spin, up spin or down spin. So you can control the up spin and down spin that way, and also you can make the superposition between the up and down spin. So you can create the superposition. So there is already development going on for the semiconductor based qubit, because then it will be much more scalable and easy to incorporate with the other things. Other than the magnetic, like you have the super like DOFs or Google's are working on mainly the magnetic based quantum computer development. So there is a lot of work going on, and this is the some example of the spin qubit, where you can confine a single dopant in the channel, and you can control the spin of the dopant by applying DC magnetic field. So you can align the spin up or down. So that is called the initialization. And you can make the superposition of the spin by sending a microwave. So if you are sending, this is the microwave, you can send the AC signal. And if you send the AC signal, that will create the magnetic field time varying. And that magnetic field time varying magnetic field will manipulate the field. So you can make the superposition of the spin. So that way you can control the spin. And how to read out the spin? So you need it is down spin, half spin, or any superposition. You need a single electron transistor. So this is the single electron transistor which can read the spin of this like single dopants, or you can confine it. You can make a quantum dot very small, and this single quantum dot can confine only one electron. So that way also you can make. But otherwise, single dopant or single quantum dot, there is many technologies are there. Also, you can make the like this one in the corner, where you can make the double quantum dots. you can control the charge either left side of the dot, right side of the dot by applying the gate bias, and you can make the superposition by applying the pulse. So that way you can make the superposition and you can read out the spin charge. So this is like a charge qubit. You can choose the charge either left side or right side, and you can make the superposition by applying the gate voltage. So there is a lot of work is going on. This is just to give you the brief, like when in the semiconductor side, what is going on. So now on the other side, like in the communication side, if you see the wire communication, like now it is a fiber optic communication, like it has started around 1888 from the Bell, so the power. And then, like the Charles Cower 2019, he got Nobel Prize because of the fiber optics. But you remember this Narendra Singh Kapani, he's an Indian, so he is from I think Ajmer. He did from the education Ajmer, then went to UK, and then he also published like his work like a long back, 1954, before the Charles Cower on fiber imaging. So he is also called the father of the fiber optics. And now if you see the fiber optic communication, like you have a transceiver which can say 100 gigabyte per second. This is the latest Intel technology, like 2020. Like per second through the fiber, you can say 100 gigabyte per second. So can you imagine? So like from this to this, now this is the current technology. And for the wireless communication, I request all the students should go through the Professor J.C. Bose life. Actually, you should read the document for the J.C. Bose. Although Marconi has shown, but same time, Professor J.C. Bose also shown the wireless communication. And during that time, you can remember, 1992, at that time, he developed wireless communication technology through this, you can see. So, and it is work up to 50 gigahertz. Now our 5G communication, even it is like 6 gigahertz or 10 gigahertz. So that time he demonstrated, and he used the point contact Schottky diode for a receiver, like galena substrate, where he used and then make a point contact Schottky contact for receiving this microwave. So we are also working on this area, like microwave detection, like more higher frequency, more than 100 gigahertz. We are working on that field, like terahertz. So now we already have 5G communication and some of the mobile phone technology, but people are going for more than 5G. Like 5G is working around less than 10 gigahertz or less than 30 gigahertz. So you want to go for beyond 30 gigahertz technology. So like more 100 gigahertz or something like that, where the data rate will be very fast. In the wireless data rate, we can say send 100 gigabyte or 200 gigabyte per second in the wireless. So that is a new technology, like the sub-terahertz communication. But there is a problem also there in the sub-terahertz. We have some absorption in the atmosphere also more in the sub-terahertz. So there is a challenges are also there, but we can solve it. So this is the recent technology in the communication. And if you see what is there inside the transceiver, which can send the 100, like a 400 gigabyte per second. So if you see, this is the receiving, and this is the like sending the data transfer. So in the receiving end, you have coming this fiber optics, you have coming huge data like 400 gigabytes or 50 gigabytes. Now this information is coming, and you want to make it within the electrical signal. So first you have to demultiplex, like a lot of information is coming, so you can divide the channel by demultiplexer, and then you read the information by photodetectors, because photodetector, like you need very high speed photodetectors, because this data is coming like very high speed. So you need high speed photodetectors, like working around 70 gigahertz or something like that. And then you have an electronic circuit, which can, because photodetectors mean it convert the live optical signal to electrical, and then you have the microprocessor which will analyze the data, and then you'll get the information. On the reverse side, how it's sending the data. So from the microprocessor, your digital information is coming, and then your electrical signal to optical. So you need high-speed laser, which will, and also modulator. So this is the laser, and then you have a modulator which can demodulate the signal. So that means you can encode the data, and then it is going through and in the multiplexer, which will convert in the single fiber, and that data is going. So this is the like a core in the communication, like all the phase, like big computer. How can you transfer the data? Like you one server to another server, very this high-speed data cable. So now come to the next things. Like this is the what world is standing in the nanotechnology side. And there is other aspect also. I'm not going those things. But as it is semiconductor nanostructure, I will not go more details. But there is a lot of semiconductor nanostructure like 2-dimensional, 1-dimensional, or 0-dimensional, and they all have different application from electronics to optoelectronics. Like if you say like the latest optoelectronics application for the is the quantum information. So you have to create the single photon. So you can create the single photon using a single quantum dot, and you can recombine single electron and hole in this single quantum dot, and then you control way you can emit the single photon, and that is useful for the quantum communication. You can polarize this photon like one polarization state and other polarized, and you can make the superposition of these two polarization, and you can send the data. So this is like a quantum communication, because that is very much important for secure data and high data rate. And also some of the nanostructure you can man-made, like is a micromotor or nano injector in your body. So this is all the MEMS technology you can make these things. And for the nanostructure, simple chemical way, other things, they have a lot of application in the sensor application, like electronic nodes or other application. And you can have 2D materials, now recent 2D materials is coming in a big way for the other application. So these are the, I'm not going details, like this nanotechnology is not only confined into the like research area, it also came to the market. So these are the physical property, how can you control the nano, but you can see now the quantum dot display, and also Samsung Note 10 Plus or more than 10 Plus, you have the battery which can charge very fast, and that has a graphene composite. So that like Samsung also launched this battery, and so other company also launching battery. And also a lot of nano composite material is used for the body of the car. So it is very lightweight but very hard, like it is very hard than the steel. So that's also going, like if you see this is the C7 Chevrolet car. This body is made of carbon nanocomposite. So there is not only the research level, it's already came to the market. And the nanostructure optical properties, as previous speaker already discussed, I'm not going details, but there are two major effects. For the metal, it is the surface plasmon resonance. That's meaning this metal nanoparticle, in the metal, there is a lot of electrons on the surface, and these individual quantum metal dots, and they create the surface plasmon. What that means, if some electromagnetic radiation is fall, then this electron will start to vibrate in the surface electrons, and these quantum, like then that create some surface plasmons, and that is also quantized. So depending upon the gold nanoparticle size or shapes, you can have different surface plasmons, so the color will change, gold nanoparticle. But in the semiconductor side, it is a different effect. So in the semiconductor, it's because of the, you have a bulk semiconductor, and this is a single atom. So in between, you can create the quantum dots, but you have to remember, there is a nanocrystal and quantum dot. All the nanocrystals are not quantum dots. When the size of the nanocrystal is less than the, or nearly comparable to Bohr radius, then it will comes to the quantum region. Or you can say, and depending upon the materials, like the dielectric constant or effective mass, your Bohr radius will be different, like this. And if you see, so that's when, if you want to see the quantum confinement effect of the semiconductor nanocrystal, you have to go down the nanocrystal less than this, radius should be less than this. So that you have to keep in mind. Otherwise, it is a nanocritical, not the quantum particle. And for the electronic properties, yes, the electronic band structure, when you go from 3D to 2D or any one spatial confinements will happen, and then it will change the electronic band structure. If you see the EK band structure of the MOS2, this is the bulk MOS2, which is a indirect band gap. But if you make a single layer MOS2, it will come the direct band gap, and you can make the LED. So people have made the MOS2 LED only possible because if you can make the direct band gap, because otherwise the direct there will be not there will be a lot of non-radiative recombination. And as I discussed, it is not only in the electronic side, you will have a lot of quantum transport, and that already for the practical application, and also for the multi-layer quantum, like quantum well structure, there are a lot of application for the terahertz or IR emission, because inter subband you can go to the terahertz. So that is for the communication you need a laser. So that's why terahertz laser is you can make. So now I'll discuss some of the work which we are doing. So first I'll discuss quickly on the optoelectronics devices. So first I'll discuss on the nanowire photodetectors, which we are working for a long time. And if you see the full electromagnetic spectrum, you can work any of these areas. Then you have to choose the proper materials, and then they have a different application. If you confine only this visible to infrared, they have a particular region application, like our camera, they have a CMOS image sensor that works only they are visible to near IR, because silicon can work up to 1 micrometer. But if you want to go more than 1 micrometer, there is a lot of application in the military and other infrared communication, and there is a night vision camera, all these things, infrared. And if you go for far infrared, they have a more interest in the astronomy, in the far infrared, like all the telescope, like NASA has, like all these telescope, they have a far infrared camera, which is made of germanium or gallium arsenide, those type of materials, semiconductor, where you dope very highly dope, and this dopant level is very near to the semiconductor conduction band, and then that energy difference is very small, like 10, 30 millielectron volt or like that. So then you can detect the far infrared light. And in the microwave, you already have mobile phone, this communication microwaves, and radio wave communication for this, for the radar, for the aircraft communication. But in this, between this, like infrared and microwave, there is another region, this is called terahertz region. Nowadays, this region is, previously this optical side, you are going from this side, infrared, and the electronic side, we have a radio wave, microwave. So in this region now, a lot of interest is going on in this terahertz region, that is like 1 terahertz, 2 terahertz, 5 terahertz, or sub terahertz. So I'll discuss little bit on that also. So depending upon the materials and which application you are looking for, so you have to choose the particular spectrum of these electromagnetic waves. And also optical sensor has a lot of application. I'm not going details. So directly I'm going to our work, which we are doing. We are doing for the nanowire photodetectors. You know, these nanowire photodetectors, they have some advantage compared to the bulk photodetectors. So they can get very high responsibility, because these surface states create a depletion layer, and that can create the photogenerated carrier. And also because of this nanowire, the transit time is very fast, so you can make the very fast photodetectors. So like in the, people have reported up to 75 gigahertz for germanium photodetectors by nanowire. So your transit time as well as the responsibility is fast. That's why the nanowire photodetector. So just I'll discuss some of the results, quickly go through. So we developed the photodetector based on WO3 nanowire. If you know the WO3, lot of group is working for the UV photodetectors, and this UV photodetector is important for the societal application as well as the UV communication for underwater. Like now people have started underwater sea communication using the UV light. So that is also important area. But for those communication, you need high-speed UV photodetector. So that's why we work on this WO3 nanowire, so which can detect the up to some microsecond. Because of the nanowires, the transit time is fast, and you can see it is detected like responsivity. It is mainly for the UV range, and then there is a sharp fall in the responsivity in the visible range. So this band, like UV band detection, and we have shown that this, because of this nanowire, transit time is very fast. You can detect the sub microsecond photo detection. And also we are working on the visible and near infrared for the easy technology. So you know the normal transistor also can as a photo transistor. You have in the UG or PG lab, you have the photo transistor already. You have for the optical experiment. But we are also working on this transistor, but not the bulk transistor, using the nanowire transistor. But we are using something different technology. It is a junctionless transistor. In a normal transistor, what you have a source N plus or drain N plus, then you have a P channel material. But if you have to go down for the gate length like very low, so then you need a very expensive technology, like if it is a 7 nanometer. So this 7 nanometer will be only P type, and then suddenly N plus. So you need a precision technology to only this 7 nanometer will not be dopant, and this source and drain will be dopant. So that is very expensive technology. So we are working on some other technology for the transistor, where you don't need to have a different dopant in the channel. You have a continuous simple same dopant, like the source, drain, and channel are the same dopant, highly dopant. But this thickness of this silicon layer very thin. It is 10 nanometer only. What will happen? So now we have a metal gate and then dielectric inside, and this is the channel silicon. Because of the metal and the silicon work function difference, you will create a depletion layer here. Now this depletion layer thickness is depending upon the doping, it will be 10 to 20 nanometer or like that. So now if I create this thickness of this silicon is around less than 20 nanometer, then it will be fully depleted. That means there will be no carrier. So you can make a transistor. Then by applying the gate bias, you can remove the depletion layer, then you can open the channel. So we work on this transistor technology, and this transistor can be used for the low light intensity detection. We have demonstrated it can be detected up to nanowatt light. So for the development of the future single photon counting, this type of technology can be used. So this is the we have demonstrated. And also we are working on the infrared region. So for the infrared region, silicon is not that much good. So we are going for the germanium nanowire detectors. And all this technology in the previous or this one, we have gone for top bottom technology. So we take a wafer and then pattern by EVM lithography. So you can make the array of detectors, anything. It is not like you take the single nanowire and then make the contact. So this germanium nanowire very high gain we have reported in the infrared range more than 1 micrometer, and it is showing very high, like you can say gain is 10 to the power 4. It is very high gain because of the nanowire. So apart from this nanowire technology, now I'll discuss some of the emerging technology. You can also work on this technology, and because this material synthesis is very easy, like 2D materials based on transition metal chalconite. Either it can be dichalconite or trichalconite, anything. So you know this work has been started after the invention of graphene by using Cos tape, and this is the material technology. And you can work any of these materials, 2D materials, and you can synthesis chemically or Scotch tape method. So there is a lot of methods, and fabrication method is very easy. But the problem is that how to see this, characterize this nanomaterial. So you need to have the Asian transmission like a scanning electron microscopy or AFM. First you check in the optical microscopy, and then device making even more challenging, and then those things. So making of this material is easy. So if you want to do research in these 2D materials, best thing is this: you synthesis by chemically or by Scotch tape method, then you characterize by optical and structural characterization, then you can publish. But you have to took the new material, not the already lot of work has been done. Because if you want to publish paper on optical and structural properties, it has to be new material. It is not like old material. But the device, if you want to work, you can still use the old material. You can design new device. But for the publication point of view, only the material synthesis, you have to go for new material. And there is a lot of new material. You should go through the literature and take one of those material, and you can buy the chemical and then start the research. I will discuss more details. And this is the some electronic properties of these 2D materials, because they are mainly important, because you can change the band gap by changing the layer number, and you can go to the direct band gap if you go to the single layer of this MOS2, MOSC2, WSC2, or WSC2 or other 2D materials. And also they are interesting because they have a spin orbit coupling. It is 150 millielectron volt. It is huge. So you can use this value electronics for making the new device using this technique. And also once you go to the direct band gap, you can make the optoelectronics device using this material. So this is the overview of the 2D material made by different 2D material for the photo detectors, and you can see the responsivity can goes up to 10 to the power 5 ampere per watt. You can imagine it is very high. Whereas the silicon, if you see the silicon photodiode responsivity less than 1 ampere per watt. By using these 2D materials, you can go very high responsivity. So these are very useful for the optoelectronics devices. Not only the photodetectors, you can go from visible to or infrared, depending upon the which material you are choosing. And also you can make the electronic devices, and you can see the mobility. So these are all the 2D materials they have made the APT. It can go very high mobility transistor using hafnium selenide or hafnium sulfide base, also WaC2 base. So depending upon your application, you can choose the particular material of this interest. So we also make this some 2D materials photo detectors. First one is the silicon MOS2 heterojunction. So we MOS2, it is not a single layer on MOS2. So what our approach is the scalable approach. We want to multiple device on a single wafer. So what you done, you take a Si2 silicon wafer, then open the window, and then make the silicon MOS2 heterojunction, and you pattern the MOS2. So we make the multiple device using this MOS2 nanostructure, and then we make the silicon and MOS2 diode, and you can say this is the silicon MOS2 diode, good diode characteristic, and you can see the like a 3 order of magnitude increase of the current when the light is fall. And we have shown this light, modulated light source, it can be gained up to more than 10 to the power 4 hertz, like more than 50 kilohertz, it can modulation, it can work. So, and we have shown this is a scalable approach, because a lot of people are working taking the single MOS2 layer, making the contact, but we make the like thousand of like in a single wafer we make the more than 100 devices and we test it. So that is our approach. And for the infrared we are choosing mainly the MOS2, so that we have made the MOS2 germanium, because germanium also infrared and MOS2 also infrared. So we make the MOS2 germanium heterojunction. Here we mainly the MOS2 flakes. We by scotch tape method we transfer on the germanium wafer and then make the device by lithography, and we make the this is the device like MOS2 germanium heterojunction. By making the MOS2 germanium, you can make very broadband response from 400 to 1.8 micron. So 400 nanometer to 1.8 micron, you can go very broadband detector using this heterojunction technique. And also responsivity increases because of the heterojunction itself creates the electric field, and that will induce the more photogenerated carrier. Now come to the recent technology. So as I told, like we are also started working on this terahertz technology. You know, this is the electromagnetic. So this is the electronic side on the microwave communication, like your mobile phone, all these are working around few gigahertz. So now you are moving more high speed data rate and high frequency communication. So that's why you are going towards this terahertz. And optical side also people are trying to do infrared and terahertz. So there is a lot of interest in this terahertz communication as well as imaging, because these terahertz, that is like in this frequency range, most of the explosive they are absorbed in this frequency range, absorption frequency. So for the explosive detection, the security regime, so you have a good interest from the DRDO, our army side also, and also for the communication. So both the security and also for the biomolecule detection, because most of biomolecules they have a good absorption in the terahertz. So if you want to learn like coronavirus also, people have shown the sensitivity in this terahertz radiation. They have shown the detection of the coronavirus using the terahertz devices, and also imaging, obviously, biomolecule imaging also. So that's why this is a very good technology for the, and this is the communication. Like now NASA also started communication for the terahertz communication link between the satellite to Earth and in between the satellite. But the problem is the Earth lot of has a water vapor, so your terahertz absorption is high. So people are thinking from the lower Earth orbit to other inter-satellite communication can be done the terahertz, because terahertz means you can send a lot of data per second, like 400 gigabyte wireless communication you can send the data, or 200 gigabyte. So that's why you people are going for the terahertz communication. And from this lower Earth orbit to Earth, you can do the normal Ka band, like it can be done like 8 gigahertz or 15 gigahertz communication. So that people are thinking, that's why this communication is important. So we also work on this, but for this communication, what you need? You need to send the data by the communication. So you need a terahertz source, and then you have a modulator. You can encode the data by modulating the terahertz signal. That's normal our mobile phone or you can do the phase modulation or amplitude modulation, and then you have a detector. So we need to develop the terahertz source, detector, and modulator to initiate this imaging or communication. So we have also started working on these APT-based terahertz detectors, but working principle is not simple. You know the normal APT, you can control the electron concentration of the channel by gate bias. Now if terahertz radiation is coupled to this channel, what will happen? terahertz is a high frequency. Now this electron in the channel, they have a plasma frequency. Now this plasma wave and terahertz, they will couple together and they will interact each other, and that will modulate the channel concentration as well as channel mobility. And it will develop a source and drain bias. And that way you can detect how much terahertz radiation is coming, and you can detect by this APT. But your channel length, like gate length of the device, has to be smaller to initiate more coupling of the terahertz radiation to the channel. So we work, so to couple the terahertz radiation in the gate, like so this is the source, sorry, this is the source, and this is the drain, and this is the gate. So to couple the terahertz, we have to fabricate the antenna. So this is the bow tie antenna on chip we fabricate, and then terahertz coupled, like absorbed by this antenna and coupled to your APT, and then you can get the source drain bias. So this is the larger image of this APT. So this is the source and drain, this is the gate. So then we make the device and then wire bond and then package, like because this is high frequency. So then we do the measurement, and we can see this is the 100 gigahertz to 1000 gigahertz. We can detect the signal of this terahertz radiation using this APT, and this is the setup. So there is a lot of scope, and you can do the metamaterial of this terahertz, like you are doing in the photonic crystal. So you can make the periodic arrangement of this metal. So this metal will absorb the terahertz radiation in this frequency, and you can use these 2D materials for making the modulator. Modulator means these terahertz signals, like any electromagnetic signal, is passing through this sample. You have to modulate the amplitude or phase. Like you can change the transmission, how much it will pass through and how much it will, but control it. So it can be done by the applying the bias. So you can deposit the 2D materials and you can change the bias voltage. So this 2D material electron density will change. Now any electromagnetic radiation, how much it will pass, that all this terahertz radiation, it will depends upon the conductivity of this layer. Now you can control this conductivity by applying gate bias or by applying pumping. Like you can shine the light by control way. Then once you shine the light, it will create the photogenerated carrier. Though your carrier concentration will change. So once this conductivity will increase, less terahertz amplitude will pass. It will be reflected the terahertz radiation. It's simple, like metal surface. You have a lot of electrons, so it will reflect the terahertz. So that way you control the amplitude modulation, and by dynamic control you can control the phase modulation. So we are working on this area also, modulator. So by using 2D materials, by optical pumping or by gate bias, you can control the electron concentration. You can change the terahertz modulation amplitude. So that we are working, and also we are working other application of this nanostructure, other nanostructure, mainly the metal oxide for the electronic nodes and biosensor. I'll show only 2 slides. So this is the overview of the, you can work any metal oxide like TiO2, molybdenum oxide, and it is very easy to synthesis by chemical method or physical deposition, and then by on the silicon, and then you work as a gas sensor. Like depending upon the which metal oxide you are using, it can be either detected ethanol or ammonia or other volatile organic molecule. So and we have shown you can array of sensor, and then you can do the signal processing, and then you can like in a room or industry, you can install this sensor like array sensor or different sensitivity, and then you can get the signal, and then you can do the signal processing. Then you can analyze the signal process from the different sensor, and then you can make how much percentage of ethanol or toxic gas are there in the room or industry. Because industry, there is a lot of application of this gas sensor. Even now in the car, if your car is heated, then you can see inside there is a lot of smell because of the volatile organic molecule. So we are working on this area by using the MO3 or TiO2 nanostructure. And also we are integrating this nanostructure on the MEMS, because some of the metal oxide, they show very good sensitivity at 200 degree or 100 degrees Celsius, not room temperature. So you have to heat up this metal oxide. And so you have to make the micro heater. So we make the micro heater. On top of that, we integrate this nanostructure, like the silicon and then TiO2. So we make the micro heater, and top of that, we have a nanostructure. So MEMS micro heater, we are also working on this area. And for the biosensor, mainly the biosensor application, we make the device and then we collaborate with the biotechnology department at IIT, other people. So we mainly make the field effect transistor based on metal oxide or 2D materials, because this metal oxide has a good charge transfer with the biomolecule. So that's why this metal oxide FET are good for the biosensor, any biomolecule detection. By FET, because field effect transistor, what is the advantage? If any small change in the surface potential, like in the transistor potential, by attaching the biomolecule, it will charge transfer will happen. So then surface potential will change and your drain current will suddenly change. So by drain current changing, you can control how much concentration of the biomolecule attached to your FET. So you can go very low level of the, people have shown femtomolar, like in the femtomole ratio, you can FET can detect. So we have shown like gram-positive bacteria detection using this FET. So we are also working other FET for the other type of application. These are the next. Like what you can do for the researcher and the college faculty, you can do. There is a lot of first thing is that if you don't want to fabricate the device, you can do a lot of simulation works on the device or photonics or optoelectronics or device. So or condensed matter physics. So these are the free software available. And I think in the college student also you can learn some of the, like you want to solve the Maxwell equation in a plasmonic structure or anything. You can learn. If you have interest, you can go through the YouTube video and then install this software. So there is a lot of free software. This is MIT free software for finite difference time domain. If you do the finite difference time domain, you can cover entire frequency range, because this is a time domain. So in the time domain, there is no frequency limit. So you can work on the visible range, infrared, far infrared, terahertz, microwave, any range. So that's why FDTD is now a very common technology, common software for solving the electromagnetic equation. And there is a for nanoelectronic device modeling, this Purdue University NEMO 05, you can, some of you can see, all of these are free software. You can download and you can do the solar cell optoelectronics device simulation. And those who have the interest in the quantum, they install this quantum espresso software to solve that, and also for the density function and tight binding model. So this is the theory, those who have a condensed matter physics theoretical, like this 2D material band structure calculation. If you have interest, you can do the simulation using this. Only thing is that you need to have a computer which has little bit higher specification, but nowadays even 1 lakh specification, 1 lakh, if you buy a computer using 1 lakh, you can get 20, like 32 GB RAM, and then those specifications, it will be more than enough for running this software. And also some of the commercial software, but you have to pay the money. So this is the well-established device simulator, Center of Synopsys or Atlas device simulator, like Silvaco, but this is expensive. Both the software you have to pay like 10 lakh for 2 license for 3 years. And also numerical solution FDTD, but this is cheap software like FDTD solver. And these are the all. I will send the PPT if somebody has interested, they can download. Actually, I will send the PPT so you can see, go through these things. And for the fabrication, as previous speaker already discussed, there is a lot of easy way to fabricate. Like one is the Scotch tape method. This is no only thing you have to buy this material. Bulk material you can online buy. Like any 2D materials you can buy online. Depending upon the material, the cost will be different. Then use the Scotch tape method. You can transfer the Scotch tape and then transfer to the silicon wafer, and then you can see by optical electrical properties of these 2D materials. Or the liquid phase exfoliation, like you can use this 2D material, and there's ultrasonic, and ultrasonic bath is very less expensive, and you can do by changing the temperature or this thing, different condition, you can fabricate different layer, like bulk to multi-layer, single layer of these 2D materials. And this is the cheapest method, chemical synthesis, and there is a lot of chemical method, like if you go through any paper, some reduction method, like you can mix up two chemical and then you can create the semiconductor quantum dots, or any different size of the quantum dot, different shapes. So, and also solvothermal method, Sol-Gel method. So there are a lot of chemical method, and that is very cheap method. You don't need that much money. Only you have to need a beaker, and if you room temperature, you don't need even heater. So beaker and then solution of this chemical. And for the chemical vapor deposition, if you want to do, that is also very cheap, because you can buy the 2-zone furnace, and you can buy it by using only 3 to 4 lakh with all the temperature control, and you can buy the powder, like you can work on the 2D materials or perovskite and any. You have to buy the chemical, and then you need a gas like either nitrogen or oxygen, nitrogen or argon gas, non-reactive gas, and then you have to need a substrate like the silicon or quartz or those substrate, and then you can do lot of nanostructure depending upon the temperature, gas flow, all these condition you can control the different types of nanostructure. So this is very cheap, like is you a lot of materials you can grow. Only thing you have to buy the chemical. And this is already previous speaker developed, discussed like this hydrothermal synthesis. This is only less than 1 lakh price. So this is like you can steel jar. So where you have heat it up, then you put the first you put inside the chemical, then you heat it up, then the reaction will take place at high pressure and temperature, and will synthesize the nano structure. So and then you can do the optical study. And this is also one type of less expensive, I can say, thermal evaporation, physical vapor, physical deposition. You can develop like within 10 to 15 lakh if you have a 10 to 15 lakh, but you can make a lot of nanostructure by grazing, and like you can make even the nanowire by grazing incident deposition. So this is also not that much expensive, but some expensive tools also there. This is very expensive, which are already there in our clinic. So this is all our IIT Delhi clean room. So we have e-beam lithography, reactive ion etching, sputtering, e-beam evaporation, all these techniques. And for the device testing, for the cheap way to do is the, like if you are making some resistive sensor, like your sensor resistance is changing by something like either due to the photo generation or by the chemical vapor or any other means. So you can buy the USB multimeter. So you can connect this multimeter in your laptop, and you can buy very cheap probe station. This is the Indian made. Like it is 1.5 to 2 lakhs. I think less 1.5 lakh is the price. So you can buy the probe station, you can put the device there, and then even through the multimeter you can measure. But if you want to device like FET characterization, field effect transistor, if you make, so you need at least 2-channel SMU. This is little bit expensive, 5 lakh. But in this equipment, you can do very low level current measurement, less than nanoampere, and low level voltage also, less than microvolt. So this instrument little bit expensive, but if you have, and it can be interfaced with the laptop or any computer. So you can just need it. So by using this probe station and this multimeter or these things, you can do a lot of electrical characterization. Electrical characterization, one you know the IV characterization, then you can measure the sensor, IV characteristic, all these things. And these are the some expensive techniques which we have in our lab along with these things. Because these things we use for the MTech student, and this is for the research club. We have the probe station, which can go up to 10 Kelvin temperature, room temperature to low temperature, and this is the semiconductor parameter analyzer. We can do the field effect transistor characterization, capacitance, imagine, pulse IV, everything. So you can do. But at least for the less expensive in this top part, college level even can set up this facility for electrical characterization. And this is the for optoelectronics, like if you want to test the photodetectors. So this is the cheap one, is the, like you have fiber coupled source. Your light will be output from a fiber, and you can use the filter to which wavelength you are coming. So this is a fiber coupled source, like a tungsten halogen source, which can give the broadband from 360 to 2.6 micrometer, very broadband. By using the filter, here you can put the filter, and then light will be coming out from the fiber, so it is easy to focus. Like you don't need any focusing of stick. So here is your device is there. You can put the fiber near to your device. So then your particular wavelength of light will come. So it is online available. You can buy online even from the Therlabs company online. So this is very cheap, and even the college level you can set up. Even if you want to do the grating experiment by this fiber laser output, you can do also that. So this is very cheap. And also you need a power meter to calibrate the source, how much power particular wavelength is coming. And you can buy the USB power meter. This is silicon phosphide, which will work up to like 1000 nanometer, from 400 nanometer to 1000 nanometer. It is price only only 20 to 40,000. You can buy this power meter, USB power meter. Even cheaper version is there, like 20,000. All are online available. So I think college level, like photo detector testing or anything you want to set up this. And this is the expensive setup, like complete photo detection, quantum efficiency measurement setup. So you don't have to do all the electrical, optical things are coming from 200 nanometer to 2 micron. You can do this, but this is expensive. But this is very cheap. And for the fabrication, if you want to Indian facility like the college faculty, if you want to use, so best way is to you do you collaborate and do the things nearby IIT or university to get the. But this is the central facility which can be accessed by anybody. And all India also now DST has started this science technology facilities map. If you please that map, some of the facilities are free. You can book the facility, but you have to go to that place to characterize your sample. So that is the only expensive, but these are free. Some of the facilities are free, like if you want to do ACM, TM, low temperature measurement, all these things you have to do. And in IIT Delhi, we also have a nanoscale research facility which is uses, but this like IIT Bombay, ISC Bangalore, they have some enough type of program where you can send your proposal, but your proposal has to be meaningful. So this is competitive, so you can go, but this is the free access. Another aspect is that there is a lot of fellowship from the INSA or INE for the faculty to join in the IIT for a summer time 2 months program. I expect some of the faculty you can get that things. And also summer research faculty, our IIT Delhi, like any faculty from the college or university come to this summer. This is free of cost. But only thing you have to apply online. So this is mainly for the application started in the April. So before April, I think March, February, maybe February, March this time, and the faculty will come to IIT Delhi to do some work in IIT Delhi, and this is free of cost. So only thing you have to register online, and then if faculty selected you, then you are come, and you can do 2 months research at IIT Delhi to get experience, either simulation or experimental, anything. So these are the, and for the student like those who are doing the BSc, what are the scope? So you can go like there are different exam, you can go like JAM, most of the student you can do, and then through that you can do MSc for either physics, astronomy, geophysics, and applied geophysics. I'd say not only the physics, some of student, if you have interest, you can go to the applied geophysics because there is a lot of placement, and also atmospheric and ocean science. So you can do the MSc through the JAM, but it is a competitive exam, you have to prepare yourself. And also the joint entrance screening test, JEST also there from DST for the ISR and IHRI. And also you have some test. I also did not know that during our time this KVPY, but it started recently. Kishore Bigyan Prasthan Yojana. So this scheme also for the not only the 10+2 student, it is also valid for the BSc student. You can give this exam. ISC conduct this exam. Now, I am there for the interview actually last 3-4 years I'm doing. So there is a lot of students from the remote college also comes in Delhi, because it is not only the like premier college students come. I have seen very raw college, some students pass this exam. So I ask students look out this exam, and most of this exam now on like online application. So you don't have to. Previously during our time, all are offline. So you have to pay post, but now it is online. You should take all opportunity. And also there is after BSc you can do integrated PhD MS at ISC. They conduct their own test and interview, although they consider this JAM and JEST. And also TIFR also conduct their own test for integrated MSc PhD. And for international, it is not required, but if somebody has interest, they can do after BSc also. If you have money, you can go this thing, international program. And job, it is very little job after BSc. So there is a like civil service, you can prepare, but you have to prepare yourself. You have to make your mind and then do. Or also some DRDO, and also combined defense service examination, Army Navy also there. And after MSc, what is the prospect? You can go for MTech, but you need to have a pass the good GATE score. Then if you do MTech, you have a lot of perspective, you have a campus placement or all these things, or you can go outside PhD after MTech also. And also for PhD in India, you have a GATE score or CSR, NET or UGC NET, and PhD admission. You can do for international after MTech or MSc. Obviously, there are different job aspects. So I acknowledge my funding agency, all these things. So thank you. So I meant, hello,
Hello.
can you hear me?
Yes.
So now this is open for the question.
Okay. So, dear participant, you have any question, please ask our speaker.
I already shown you the email ID, so you can send me email also. And there is a lot
Yes.
of
Yes.
prospective for the faculty also in India nowadays, because the government is taking initiative for the faculty for the college and university to more research oriented. And I have already shown you lot of prospects are there.
Okay. So, thank you, our speaker, for delivering his very good speech and good lecture, and very much different kinds of job opportunities and teaching, or the difference of scope for the newcoming student for the BScs. So thank you again, our participant and the speaker. So now I requested to Dr. Sri Arubratam Chakraborty to say some things and end our seminar.
Am I audible?
Yes, yes, yes. I'm getting your voice.
Honor, Honorable Principal of our college and the Chief Patron of this international webinar, Dr. Montu Kumar Das, the Head Department of Physics and convener of this webinar, Dr. Kaushik Dey, our most valued speakers for this webinar, Professor Karthik Ghosh, Professor, Department of Physics, Astronomy and Material Science, Missouri State University, United States, and Dr. Shamaris Das, Associate Professor, Center for Applied Research in Electronics, Indian Institute of Technology, Delhi, all my colleagues, respected participants, and friends. It is my privilege to have been asked to propose a vote of thanks on this one-day international webinar on recent research trends in nanomaterials and devices organized by Department of Physics, Shankal Vidro Sharda Shatavarshik Mahavidyalaya. I, on behalf of the Teachers' Council and the organizing committee, extend a very hearty vote of thanks to the distinguished speakers for sparing their valuable time and gracing today's event and sharing with us their findings and thoughts. It is very late at night in the United States, and I express our gratitude to Professor Karthik Ghosh for his engrossing talk. Professor Ghosh, in his speech, Nanostructured Materials for Applications to Clean Energy, showed how nanostructured materials can be used for various materials and applications. He spoke about these materials' electrical, magnetic, optical, and mechanical properties and their biocompatibilities. Professor Ghosh also talked about various sustainable energies, including the use of solar energies, and how these energies can be used for the benefit of the society. Thank you, sir, for your inspiring talk. We are thankful to Dr. Shamaris Das for his fascinating talk. Dr. Das, in his talk, Semiconductor Nanostructures for Electronic and Optoelectronic Device Applications, spoke on the various aspects of the electronic and the optoelectronic devices. He also informed us about the numerous features of the semiconductor nanostructures. Dr. Dash beautifully enumerated what we can do with these devices. Thank you, sir, for your captivating and absorbing talk. I would like to express our gratitude to the President of our governing body and member of West Bengal Legislative Assembly, Sri Srikanta Mahato, for his strong support for every academic endeavor of our college. I also convey my gratitude to all the members of our governing body for their continuing support in organizing academic programs like this one. I express our thankfulness to our principal, Dr. Montu Kumar Das, for the true inspiration behind this international webinar. It is because of his stimulus and encouragement that various departments of our college are undertaking similar ventures. Thank you, sir, for your support. I thank Dr. Kushike, the head Department of Physics, who worked as the main force for this webinar. All the technical aspects of organizing this event and streaming it live on YouTube are single-handedly done by him. I also congratulate him as his department is the first one in our college to organize an international webinar. I extend my thankfulness to all teachers, students, and staff of our college for making this webinar a grand success. I conclude my speech by thanking all the esteemed participants of this webinar, without whose presence and participation this webinar would not have been possible. Thank you so much for your participation. Thank you all and have a nice and safe day.
So thank you. Thank you again, all of the participants and our speaker and delegates and students. So now I end the seminars, and the feedback link is already sent in the chat on YouTube and this Google Meet. So fill up it, and after 2 days you will get the certificate also. Thank you very much.
Thank you.
Thank you.
Thank you.